clamping a red-hot iron block onto a machine and hammering it. You can see that as the glowing red metal deforms, a layer of dead skin also peels off its surface. It's not just from hammering. If you twist a red-hot iron block back and forth, fragments of debris will continuously flake off. Have you ever wondered why metal flakes off debris when it's being forged? And what exactly is that fallen debris? These fragments are actually metal oxides formed when the hot metal comes into contact with the air and undergoes an oxidation reaction, along with some non-metallic impurities. This layer of iron oxide is brittle and hard, with a porous structure, and its own strength is not high. Its bonding force with the metal body is very weak, so when the parent iron is impacted and deforms, it easily turns into slag and falls off. Therefore, this flaking is not a bad thing. It can not only remove impurities, but if the outer iron oxide is hammered into the steel's interior, it would negatively affect the steel's quality and appearance. However, during forging, every time the metal is heated, a layer of oxide forms, causing loss. Theoretically, if you endlessly repeat the forging process, this piece of iron will get smaller and smaller. Therefore, to prevent the metal from continuously oxidizing during forging, workers will also sprinkle an appropriate amount of borax on the metal surface. At high temperatures, it not only melts into a glass-like liquid to cover the metal surface and isolate the air, but it can also act as a flux. It undergoes a chemical reaction with the metal oxides that have already formed, making it easier for them to detach from the metal surface during hammering, thereby increasing the success rate of forging. In addition, some metals need to undergo quenching after forging. The red-hot forging is placed into water, accompanied by dense white smoke and the boiling water. The steel gradually cools down. So, what exactly is being quenched? Is it just about cooling the metal down? Quenching is a method of heat treatment for metallic materials. At high temperatures, the carbon atoms inside the metal form a stable structure called austenite. Quenching is intended to instantly freeze this relaxed, soft state. During this rapid cooling process, the internal material structure of the metal changes again, transforming from austenite to martensite. Its crystal structure is highly distorted. The interior is filled with immense stress. This is reflected in the macroscopic properties as extremely high strength and hardness. So, quenching is both for cooling the workpiece, but not merely cooling it down. Increasing the strength is the key. Interestingly, besides water, oil can also serve as a medium to cool the workpiece. Water quenching has an extremely fast cooling rate, achieving the highest hardness. It is the first choice for tools like files and drill bits, but its internal stress is also too great, making it prone to deformation or cracking. Oil quenching has a relatively gentle cooling rate, allowing the metal's internal structure to transition more gradually while gaining hardness, and also has better toughness. However, quenching is not the end. The martensite obtained after quenching is hard, but also very brittle. It can easily snap when encountering something hard. Therefore, the craftsman immediately follows up with tempering, which means reheating and cooling it again at a suitable temperature. This achieves a balance of both hardness and toughness, allowing the metal to reach its perfect state. If you clamp a metal rod with pliers and shake it back and forth, the rigid metal will soon snap in the middle, almost like soft taffy. Even if the shaking motion is very small, it cannot escape the fate of breaking after prolonged, repeated movement. In real life, actually, if we want to break a wire, our instinct is also to bend it back and forth repeatedly. Have you ever wondered why a rock-solid piece of metal gives in after repeated bending? The answer is metal fatigue. Place an iron rod onto a high-frequency vibrator, and then increase the frequency. If you observe the rod closely, even though we can barely see the rod vibrating with the naked eye, as time slowly passes, a crack begins to appear in the middle of the rod. The crack grows larger and larger, and quickly breaks into two halves. This is actually because, under repeated stress, tiny dislocation movements and accumulation occur within the metal's crystal lattice. These dislocations ultimately form microscopic cracks at points of stress concentration. The higher the stress, the fewer cycles the metal can withstand. Once the fatigue limit is exceeded, the consequences are unimaginable. In the 1950s, the Comet, the world's first commercial jetliner, mysteriously disintegrated in mid-air one after another. After ruling out factors like explosives, engineers ultimately discovered fatigue cracks at the square corners of the cabin windows. A jetliner flies at an altitude of 10,000 meters where the air pressure is low, but the cabin must maintain normal pressure. Therefore, the fuselage is subjected to a massive pressure differential, especially near the windows. As points of stress concentration, their load would be greater than in other areas. At this stage, the square windows became deadly. We can simulate the stress flow path. Compared to a circle, the square window clearly has more obstacles, and the stress is more concentrated at the window's sharp corners. In addition, the aircraft used a riveted assembly method, which could cause microcracks in the aircraft's skin. Due to these various factors, this catastrophic accident occurred. This is precisely why, to ensure the load is transmitted uniformly, subsequently developed airliners mostly began adopting a circular window design. Have you ever considered what methods can be used to combat metal fatigue? Changing the shape of the airplane windows, as mentioned, is one. Another is a method of fighting fire with fire, which is precompressive stress. Since tensile stress is the culprit for fatigue cracks, we first introduce a strong layer of compressive stress onto the metal surface. When the external working load generates tensile stress, it must first counteract this preset compressive stress layer. Shot peening is an example of this process. Countless small steel balls are shot at high speed onto the part surface. This not only cleans and polishes the surface, but also creates a layer of compressive stress that locks the surface, preventing the cracks from starting. This can significantly raise the metal's fatigue limit. However, relying only on process prevention cannot guarantee complete safety. In practical use, detecting whether the metal has fatigued is also crucial. For certain ferromagnetic materials, we can use magnetic particle testing. If the metal has defects like cracks, a leakage magnetic field is produced at the defect site after the material is magnetized. This attracts magnetic powder, forming a magnetic indication. There is also ultrasonic testing, which involves sending high-frequency sound waves into the workpiece. When the sound waves encounter a defect, they reflect. Technicians can then analyze the reflected waves to determine the location and size of the defect, and intervene in time to perform maintenance.